Taha Sultanagai, Assistant Professor at University of Illinois Urbana-Champaign, and I will be chairing the last session of the day, the only thing left between us and the banquet. So we have 4 presentations, and we're starting with the first one. Rafael is a research engineer and PhD student at the Wireless Networking Group at IMDEA Networks in Spain. His research interests on software-defined radios, FPGAs, and signal processing for wireless communications. And today he will be presenting HELIX, the high-speed real-time experimentation platform for 6G wireless networks.
Thank you. So, hi, my name is Rafa. I will present HELIX. And this is a collaboration between IMDEA Networks and from Spain and TU Darmstadt from Germany. So I would like to start my presentation by asking this question: what should we expect from wireless networks of the future? Probably what comes to everybody's minds is basically a higher capacity and higher bandwidth for the demands of new applications. And on the other side, what we could expect is the integration of sensing capabilities in the network. And for that, we need experimentation platforms that can keep up and validate all of these features. So the problem is, as of now, open source platforms are not keeping up the pace of the next gen wireless networks. So we have 2 kinds of open source platforms available in the community. We have platforms that are based on software mainly. They can perform in real-time operation, and they are mostly connected to. They can be connected to real networks. But the problem with this kind of platform is they will only allow low bandwidth configurations, so no more than 100 megahertz. And on the other side, we have FPGA platforms that they can go up to 2 gigahertz of bandwidth, but they don't have real-time operation. Basically because they rely on memory-based design. So what they do is they store the IQ samples in their memories, and then they send it to a server, and then they do offline processing. So we need wireless experimentation platforms that can combine these 2 features: real-time operation and high bandwidth. So also the wireless network demands are not only growing, but also they are diversifying. So that's why we need to be able to decide what is running in hardware and what is running in software in our networks. So if we decide to go for a software-based, or we decide to use more part of the software in our implementation, we will have more flexibility in our design and a quicker deployment. But this comes with a trade-off. The problem with this implementation is the less functionalities that you have in your FPGA, the more data that you will have to send over your front-haul interface. So that means that you will have a bottleneck if you want to target high bandwidth configurations. If in the other case you want to run more or you want to run more functionalities in your FPGA, you can target higher bandwidth configuration and lower latencies. But the problem with FPGAs are rigid, and they don't allow for the flexibility that you could have using software-based design. So we need platforms that can dynamically change the split to enable better experimentation and adaptability. And this is a bit in line with the task disaggregation that is a key feature of the Open Random Access Networks, or RAN. So the take-home message is we need platforms that are high bandwidth, that that they have run in high bandwidth. They can do real-time operation, and they are flexible and scalable enough. So with that in mind, we introduced HELIX, which is a platform that combines hardware and software. We introduce in this platform a flexible crossbar that can dynamically reallocate the functions of the file layer blocks between software and hardware. We also develop a custom front hole so that it enhances the flexibility of the system. And on the other side, we've also implemented a interface library based on C++, so that we can integrate HELIX in any kind of platform. And last, we developed these processing blocks to be able to operate in different bands, such as sub-6 gigahertz or millimeter wave. Now let's take a look at the features of the blocks of HELIX in more detail. So if we take a look at the processing blocks, we've implemented all of the 5G physical layer in the FPGA, so that these kind of blocks can work in different numerologies. So we can reuse them for transmitting a FR1 and also an FR2, which is sub-6 millimeter wave. We can also reconfigure in runtime the number of reserve blocks, the modulation, and the subcarrier spacing. We perform multi-parallel processing so that we can relax the clock timing in the FPGA, and with that we are able to achieve 400 megahertz of bandwidth. And all of these blocks are interconnected using AXI standard interfaces. So it brings more flexibility and more modularity to the system. So a bit in line with this, I will introduce the crossbar, which is a key enabler for multi-split functionality. What is this crossbar doing is connecting all of the processing blocks in the FPGA, so that we can decide how to route all of the data path, and we decide what is running in the in hardware and what is running in software. We can dynamically change this configuration in around 50 microseconds, and it also brings flexibility to the system, to the network, because we can add new features to the network. Like, for example, let's say for some reason you don't want to use your OFDM modulation in your physical layer. So what we can do is we can remove the OFDM modulation from our FPGA. We can generate OTFS modulated data because you want to try this for your research, and you can feed it directly to the filter and DAC, and you will be having OTFS in your physical layer. So that's an example of how quick you can change your physical layer, your physical layer in HELIX. So we've also made this custom 10 gigabit Ethernet front hole interface. We made it. We made it to be outside the standard, basically because we wanted to be able to use it regardless of the split configuration. And also this front hole interface is based on UDP ports, so that we can divide our data path. Our data path, one for streaming data, one for sending control messages that will be processed by the processing system, and that will change the configuration of the blocks, and also want to extract information from the physical layer that is information such as channel state information, SNR, or micro Doppler. So we can select what kind of data do we send to the network. On the other side, we have a interface library that is based on C++. It's a lightweight C++ wrapper. It's running on a. It can run on any 10 gigabit Ethernet capable PC. It handles the whole front haul, the signal processing blocks and its configuration, and it can be integrated in any application. And if you can take a look at here at the code, this is an example of how quickly, in a few lines of codes, you can deploy HELIX in any application. So we made HELIX. We implemented HELIX using Xilinx RFSoC, this model, which is CCU 208. But we can run HELIX in any other kind of platform because we made it based on the standardized interfaces. So it can be run in another type of FPGAs. And if we take a look at what kind of resources do we use for HELIX, for one instance of HELIX, using a transmitter and a receiver, we see that we use around 20% of the DSP and logic blocks. So we have margin to add more functionality in the FPGA, and like for instance, we can use just one board to add more instances of HELIX and do carrier aggregation. Block RAM would be mostly used by large buffers, so that we can, this won't grow in the same way as DSP or logic blocks. Also, we measure the latency of our signal processing blocks. We see that in the transmitter we have less than 40 microseconds, and it's dominated by the OFDM modulator. And in the receiver we have 100 microseconds, and it's mostly dominated by the LDPC decoder. We've made this analysis of the 5-layer performance on HELIX by using 2 nodes of HELIX and transmitting over the air using different type of front ends. We tested in sub-6 gigahertz, 28 gigahertz, and 60 gigahertz over the air with front ends, but at the same time, HELIX can be connected to any kind of front ends from different frequencies, such as FR3 band or sub-terahertz. And here you can see in this picture, in the pictures below, you can see how we send modulated data over the air, and even in millimeter wave, we have a very good constellations, even for high order modulations. We made an analysis of the bit error rate, comparing software and hardware for different modulations. And as you can see here, you can see that hardware is performing slightly worse compared to software, which is an expected thing because hardware, because of the quantization that is happening in hardware compared to infinite precision of software. So this is an expected behavior. If we also measure the front haul overhead for different hardware software splits, and we can see that if we go in this picture from left to the right, the right will mean that more functionalities are running on the FPGA. So this will mean in here we will be sending bits, while here we'll be sending IQ samples. So this means that when we send bits, we reduce in 90% the front haul overhead in our front haul interface. We've also measured the end-to-end latency of HELIX. We made it by using 2 nodes of HELIX We send a message, we wait for a reply, and we measure the time difference. And we did the same experiment for 40 seconds. And the results show that we have a 550 microseconds of median latency, and 90% of the time we are below 625 microseconds. So we can say HELIX is compatible with ultra reliable low latency communications. And also we tested HELIX for sensing applications. In this example, what we do is we set HELIX in a monostatic radar. We configure HELIX to run all of the physical layer implementation in HELIX. We send data and we receive the channel state information back. And with this channel state information, we measure we can extract the micro Doppler of a person moving back and forth. And here we can see how the velocity of this person, the direction is changing. So this is an example of sensing application that you can run on HELIX. What are things? There are other things that you can do with HELIX, such as, well, I briefly mentioned about carrier aggregation. In this example, you can see how we achieve almost 2 gigahertz of bandwidth just by using one board with one FPGA. We can also perform multi-static and multi-band ISAC experiments, and we also can use HELIX as a hardware acceleration within a network by offloading an isolated function like LDBC decoding, just by sending LLRs and receiving the decoded bits back. And for future work, we are planning to synchronize multiple boards to target even more even higher bandwidth configurations. We're planning to do MIMO communications and also integrate the platform with SRS Run and OpenAI. So to end up, the HELIX is open source. So HELIX is a platform that combines real-time operation and high bandwidth. It can change dynamically the functional split thanks to the crossbar that we develop, and also has the ISAC and hardware acceleration capabilities that enable advanced 6G application. And for last is scalable, and and you can check our GitHub to check our implementation. Thank you.
Questions? I can start with a question while others warm up. So if I understand correctly, because you have a set of predefined options in the FPGA, you need to select which one to use in real time. How about we want to just modify the configuration of one of them? I think one of the examples was like modifying the modulation. So do we need each one of them to be predefined, or can we just select for example, a PSK like 16 versus 18 on the go?
So the thing is, with FPGAs, the time it takes to really deploy a new functionality in an FPGA compared with software, it can take weeks compared to the time that you can take to build it in software. So the whole idea is, if you can always bring new functionalities to the FPGA, but the idea is most of the people are more familiar with software when developing new application. So our idea is you can have both possibilities. You can have the performance of the FPGA, but also you have the possibility to bring new functionalities just by coding it in software in your MATLAB or in your whatever application.
Hi, thanks for the interesting talk. I'm Mehdi from UCI. So the question that I has is, can we use this HELIX framework with the older generations like 4G systems and other things like that? Since it seems that we need to rewrite the distributed unit of the radio access network in order to be able to connect to the system, right?
So you mean if we can directly connect it to a network of 4G?
So let's say we are gonna use some of the existing open source radio access network like the open air interface, right? And we wanna use your system. Do we have to rewrite those APIs for connections, or is it compatible already?
No, I wouldn't say it's compatible out of the box. What you can, I guess you could use it for only doing FFT, but no, I wouldn't say it's compatible out of the box. So that's yeah.
Thank you very much.
Thank you.
Let's thank our speaker once again. Move on to the next presentation.